Hi everyone. So in this video, I want to give a brief overview of what capacitors are and some of the ways that we'll talk about capacitors as we move forward here. And I want to define capacitance. So briefly, the most basic definition of a capacitor that we have is any sort of device that stores charge. Let me write that down. So a capacitor is any device that stores charge. And that's sort of the important thing. The most fundamental thing to realize about what a capacitor is doing is that it's just storing charge based on some process. And we'll talk about the processes that end up pushing charge into capacitors shortly here. But we quantify the way that a capacitor stores charge with capacitance. So capacitance is defined, I'm going to use this thing to be defined as or equivalent to the capacitance of a capacitor is a ratio of how much charge it can store over how much potential difference there is in the capacitor. And I think this may not make a whole lot of sense right now, but we'll work through an example here shortly where hopefully it will make a little bit more sense. One thing to point out here is that the units for capacitance are pretty weird. The units are going to be, so if it's charge, the units are Coulomb and voltage on the bottom, so that's volts. So coulombs per volt is the unit of capacitance. That's called a farad. So units of capacitance is a farad. And sometimes it's abbreviated as an F, usually as an F. Okay, so if you look here on the left side at the top, there are some examples of what capacitors look like in the wild. There's lots of different types of capacitors and they have lots of different shapes and sizes. You'll notice that all of the ones that are included here have two wires going to some central body. So normally the way you would use this is you would hook up some system to this. So you might consider hooking up a battery to one wire, the positive terminal of a battery to one wire, and ground to the other wire to create a potential difference in this capacitor. And that's what enables us to store charge. So by creating a potential difference, you're getting some V. And then based on the capacitance, you'll be able to store some Q. If you look down here, there's a little arrow down there. So this is an example of a classic capacitive system. This is called a parallel plate capacitor. So let me write that. Parallel plate capacitor. Parallel plate capacitor. It's a classic example and it's a good way to understand what capacitors are doing. So imagine I've got two parallel plates, which is a system that we've studied at some length at this point. And so there's some charge on each of the plates. Let's say the magnitude of the charge is the same on each plate, but on the left plate here, the charge is positive, and on the right plate here, it's negative. Those plates are parallel to each other. That's why it's called parallel plate capacitor. Oop, I meant to write capacitor instead of capacitance here. Let me do that. Parallel plate capacitor. And each plate has the same area. They're flat plates. They both have area A. They're held some distance d apart. So I've actually established a coordinate system here because that will be useful to me in a second. So I'm saying the left plate is at x equals 0, the right plate is at x equals d, and the positive x direction then goes from the left plate to the right plate. We know that there is some electric field in between these plates. There should be, because positive charges would want to move to the right when they're in the space between these two plates. So there should be an electric field to the right. And the approximation that we're going to make is that these are effectively infinite plates, so that we can just take the electric field to point straight right, and we're not going to consider any of the edge effects of getting near the edge of these capacitors. That's a simplification in the model, but that's what we'll work with. So if I wanted to understand the capacitance of this system, I'd want to know something about how the charge here relates to the potential difference between the plates. So if I'm looking at capacitance, C is equal to Q over V, this refers to, the Q refers to charge stored on each plate. And the V refers to the potential difference between the plates. Potential difference between plates. And we're going to see that pop out of an equation in a sec, but I want to prepare you for what we're talking about and looking at here. So how do we get to the capacitance of a system like this? Well, the way to start is to figure out what the potential difference between the plates is. So let's try to do that. So the electric field goes to the right, we know that. But we can also write down its magnitude. We solved that problem before spring break. So the electric field between two parallel plates has a magnitude that's sigma over epsilon naught, perpendicular to the parallel plate. So that's the x hat direction in this case. For us, sigma is just Q over A, because that's the area charge density, assuming that the charge is uniformly distributed on the plates, which is fine. So we could write the electric field as Q over A epsilon naught x hat. I won't solve for that again. You can get that using Gauss's law for each of the plates and then adding up the contribution from the electric field from the positive plate and the negative plate. So if you want to go back and review that, you can. But if we know the electric field, then we can get the potential difference between the plates by just integrating the electric field moving from one plate to another. So what I'm going to do is I'm going to calculate the potential difference between the plates, which is E dot dl. And I'm going to integrate going from the lower plate to the higher plate so that I get a positive value at the end. And you could do it the other way if you want, but the capacitance is defined as a positive value anyway. So I'm just going to integrate from where I know potential is lowest to where I know it's highest. So I should get a positive potential difference value when I do that. So what I'm doing here is I'm integrating an electric field, which is the positive x hat direction, dot dl. And dl is always just dx hat, or excuse me, dx I hat plus dy j hat. So if I take the electric field dot dl, I should just get E times dx here. So I should get minus integral q over a epsilon naught dx. And if I'm integrating from the negative plate to the positive plate, then I'm starting at d and going to 0. I can pull everything out of the integral, q, a, and epsilon. Those are all constants. So this integral just becomes minus q over a epsilon naught integral dx from d to 0. So if I do that dx integral, I just get x. And then the upper bound is 0, the lower bound is d. So I get an extra minus sign from the lower bound. So you can check my work on that integral, but I should get qd over a epsilon naught as delta v. Okay, let me scroll down here a little bit. So this is a relationship between the potential difference between the plates and Q. And capacitance is that relationship. If I look here, C is this ratio of Q to V, and we have V and Q in here already. So if I rearrange this, I can just get the capacitance. So the capacitance is, if I just take Q over delta V, I get the capacitance. So if I do that, I have to divide by, I have to take this equation, divide both sides by delta V, and then divide both sides by d over a epsilon naught. So if I do that, I get a epsilon naught over D. And that's the capacitance of a parallel plate capacitor. With these assumptions, like we're taking the plates to be infinite. This is capacitance for a parallel plate capacitor. So one thing to notice about this equation is that the capacitance is only dependent on the geometry of this capacitor. So it only depends on the area of the plates and how far apart the plates are in this case. If we had a differently shaped capacitor, we would have a different capacitance, but the capacitance would still just be based on the geometry of that capacitor, which is something interesting to think about and to know. So we should be able to figure out what the capacitance of a system is just based on its geometry, which might come up for us later, but it's just something to know for now. But beyond that, this equation is a little bit opaque, and I want to plug this into an application so you can see how this works and how the capacitance operates. So let me scroll down a little bit further. So imagine that, let me leave this here. Okay, so imagine that now what I do is I take this capacitor. So I take my parallel plate capacitor, I'll redraw it here. It's not the best in the world, but it's okay. And I now hook it up to a battery. So here's a battery. And let's say here's the positive side of the battery, here's the negative side of the battery. So I hook up one plate to the positive side of a battery, one plate to the negative side of a battery, and that there's some potential difference between the two terminals of this battery. So there's, say, a potential difference V from one side to the other. So the positive terminal is held at potential V relative to the negative terminal. That means that the capacitor plates should be held at that same potential difference. If I hook up the left plate to the positive terminal, that should be held at a voltage V relative to the right plate. So this potential difference should be V right there. Okay, and when I do this, but also what happens is because it's a battery and the battery has a constant voltage, then the potential difference between the plates does not change. And that's something to remember here. So what happens when we plug this system into the battery? Well, charge will start to flow onto each of the plates. So if we imagine like the current is positive, like there's positive charge carriers, you can imagine positive charge flowing onto this plate, positive charge flowing that way, and positive charge flowing off of this plate. As the positive charge is pushed away from the positive terminal of the battery and attracted towards the negative end of the battery. And the effect is that we just build up a bunch of positive charge here, and we build up a bunch of negative charge here. Alternately, you could think of charge carriers being negative, and then we would have negative charge carriers moving this way. So negative charge carriers moving that way, negative charge carriers moving that way. So negative charge carriers being attracted to the positive terminal of the battery, leaving a net positive charge on the left plate, and negative charge carriers being repelled from the negative terminal of the battery, leaving a buildup of negative charge on the right plate. But either way you can think of it, you get the same result. So when you turn the battery on, the battery pushes charge around in the circuit, but eventually it can't push any more charge onto these plates. So as more and more positive charge builds up on this plate and more negative charge builds up on this plate, eventually some equilibrium is reached where even though the battery is pushing positive and negative charge around here, it just can't move charge anymore because there's already such a large buildup of positive charge on the left plate and negative charge on the right plate. If you imagine the positive terminal in this equilibrium position, if you imagine the positive terminal repelling a positive charge, but the left plate now also repelling that same positive charge with equal magnitude, then you get a system where nothing is moving anymore. And that's kind of what happens very quickly when you plug a capacitor into a battery. Just charge stops moving around and you get to the steady state where charge is held on the capacitor. So how do we interpret this? Well, up here we have this equation for capacitance. So if you think about what this would mean in this context, it says, when I have this battery and I plug this battery or I hook this battery up to my capacitor, some amount of charge will collect on each of the capacitor plates. Because remember, this Q in the capacitance refers to the charge that collects, the positive charge that collects on the left plate, and also the negative charge that collects on the right plate. The magnitude is the same. So if I have a fixed voltage, the charge will change on each of these plates depending on the capacitance. So if I'll just write capacitance again here. Epsilon naught is a constant. So as long as we don't put anything in between the plates, and we'll talk about that later, epsilon does not change. But we could, in principle, change the area of the plates. So if you imagine making the area of these plates larger, then the capacitance would go up. And if the capacitance goes up, but the voltage is fixed, then the charge goes up. So here's another way of thinking about capacitance. If the voltage is fixed, but the capacitance goes up, the charge has to go up. And the physical way to think about that is if we increase the area of the plates, there's just more space to fit charge on the plates. So you don't get as strong of repulsion because the same amount of charge wouldn't be as dense on a larger plate. So you can shove more charge onto each plate. So if A goes up, capacitance goes up, and charge goes up. This is because you can shove more charge into more space on the plates. So that's one way to change the capacitance. The other way to change it is to change the distance between them. So that distance d that we had in our original setup of the problem. So d is now inversely related to the capacitance. So if d gets smaller, the capacitance goes up. So why would that be? Because if I shrink the distance between these two plates, they're getting closer to each other, and then you get a larger polarization effect from the opposite charges on each plate. So if you imagine taking the positive charges on this plate and moving them closer to the negative charge on the left plate, then those positive charges feel a larger attractive force to the right. And that means that you might be able to push a little bit of extra positive charge in there because that extra positive charge is being attracted a little bit more to the negative charges on the right. And likewise, that process works in reverse for the charges on the right plate. The negative charges, as those positive charges get closer, feel a stronger attraction pulling them to the left, which pulls a little bit more negative charge onto the plate. So that means that if the distance between the plates goes down, the capacitance goes up and the charge on each plate also goes up because you can shove more charge onto the plates because there's increased polarization. There's a larger polarization effect between the plates. So you can shove more charge on the plates. Into the plates because of greater polarization. Okay, so I think that's the way to think about capacitance. This is the simplest possible way to think about capacitance, but it's sort of useful because you can really see what Q and V mean in this system and how capacitance affects them. I hope that helped a little bit. And as we go along, we'll talk more about capacitors, but I think remembering the physics of what's happening in a capacitor, that the way that charge is moving around and the way that the spatial relationships between charge impact the behavior of a system is really, really important because we'll keep abstracting and abstracting and abstracting, which is really valuable for solving more complicated problems. But at base is always just this relationship between like the attraction that positive charge has for negative charge and negative charge has for positive charge, and the repulsion that like charges have for each other. So hopefully that helps, and I will talk to you soon. Okay, bye.